In this video, I'll be introducing some applications of the fundamental group of this circle that we calculated last time. The calculation of this fundamental group is actually very important, and it has many applications to important theorems and their proofs. One such important theorem is the Fundamental Theorem of Algebra, which you might not have expected. So first of all, the Fundamental Theorem of Algebra basically says that the complex numbers are an algebraically closed field. What does that mean? Well, that means every polynomial, we'll call it f of z, and we'll assume that the first coefficient is 1, because if it wasn't 1, you could just divide through by that first coefficient. Z to the n plus a1, z to the n minus 1, all the way down until an. So we have this arbitrary polynomial, which has coefficients in C, and it inputs values of C. And we have it that n, which is the biggest value, is not equal to 0, which is basically saying it's not a constant polynomial, means that f of z has some root, which means there exists a z such that f of z is 0. So every polynomial in C has a root in C. So how on earth do we prove this using the calculation of the fundamental group of the circle? So we're going to prove this by contrapositive, meaning we will start with the assumption that f of z has no root, then we will prove that n is equal to 0, meaning it's a constant. Alright, so suppose f has no root. Then we can go ahead and construct a new family of functions. I'll call it gr of z, which is going to be equal to f of r e to the 2 pi I z divided by f of r. And then we're going to divide this entire thing by the magnitude of the same thing. And this is going to be for r bigger than or equal to 0 in the real numbers, and z is your complex input. Now, because we know that f has no roots, we know that this is well defined, because this denominator will never equal 0, this denominator will never equal to 0 either, because it all involves just f. What is the importance of this? Well, if I do g0 of z, what does that equal to? Well, that's that's just going to turn out to be 0, because you have r times other stuff, r is 0. So that's f of 0 over f of 0. And then we divide that by the magnitude of f of 0 over f of 0. And so you just get 1. You get the constant map for this. So that means that g0 is the constant map at 1. And then the rest of these grs are like a homotopy, which means that gr is homotopic to E1 for every one of those r's. This is going to be important because we're going to use these grs and show that they're homotopic to the loop that goes around n times. For that to be the case, it has to be homotopic to E1, which then n is 0. And we have our contrapositive. How exactly do we approach doing that? What we do is choose a sufficiently large R0, and sufficiently large means that it is strictly greater than the magnitudes of the polynomial summed up. Now, the reason why we want to do this will become apparent a little bit later. Let's suppose we have some z, an element of the complex numbers, and we have it that its magnitude is equal to R0. What can I derive from this? Well, we're dealing with a polynomial which has a maximum exponent of n, a degree of n. So we should look at the magnitude of z, because we know that relates to ours, to that degree power, z to the n. The magnitude of z to the n is the same thing as r0 to the n. But I can split up r0 to the n into r0 to the n minus 1 times r0. Now, the reason I want to do this is because we have this bound on r0. So we know that this has to be bigger than converting this r0 to the n minus 1 back into z, so the magnitude of z to the n minus 1, and we multiply it by the sum of the absolute values of the coefficients. Where do we go from here? Well, we go ahead and use some properties of absolute values. We know that the sum of many different absolute values is bigger than or equal to the absolute value of that sum. And so we know that this is going to be bigger than or equal to the absolute value of z to the n minus 1 times the quantity of a1 plus all the way up until an. And so we just use the identity that absolute value of x plus absolute value of y is bigger than absolute value x plus y. And we also use the fact that the absolute value of x times the absolute value of y is equal to the absolute value of x times y. Those are just the two basic properties of absolute value we use there. Now that we have this, what I'm going to do is do another greater than or equal to. You'd imagine I distribute this normally, so I would have a1 z to the n minus 1 plus a2 z to the n minus 1 all the way up until an to the z n minus 1, but that would be equal. And we actually want this to be more similar to the original polynomial we had. And so instead of doing that, what I'm going to do is to make this less than what we had before, I'm going to reduce the power on each of these until we get the sum of a1 z to the n minus 1 plus a2 times z to the n minus 2 plus a3 times z to the n minus 3 all the way up until an times z to the 0, which is the same as an. And so the reason I can do that is because when I reduce the power of z, then it becomes a smaller value. It has a smaller magnitude. Now, what all of this tells us is that we can construct a new family of maps I will call ft of z. Now this is going to be equal to z to the n plus 1 minus t times this polynomial we have right here. Now, I know that this has no roots for the absolute value of z is equal to r0, and for 0 less than or equal to t less than or equal to 1. Why do I know that? Well, I know that the magnitude of zn is strictly bigger than the magnitude of this section of the function. So what that means is that there's no way they can cancel out to 0. And then, because these coefficients are between 0 and 1, that means all of these will have magnitude less than strictly z to the n. Which means that this thing will never be able to reach 0. Because if this has a bigger magnitude than that one, they can never perfectly cancel out. In order for them to perfectly cancel out, they have to have the same magnitude, and so it has no roots. Now, why specifically did I want to get this polynomial out the other end? Well, f0 of z is going to be equal to z to the n plus a1 z to the n minus 1 all the way up until an, which is f of z. And then f of 1 of z is going to be equal to, well, that goes to 0, just z to the n. And so this is a nice transition that takes you from your original polynomial just to z to the n. Given this, we can go ahead and construct that n loop that we wanted. The way we do this is by defining a third new family of maps, ht of z. And ht of z is going to be equal to basically this, but we will replace f with ft. So we have ft of, now instead of r, we're going to do r0, e to the 2 pi I z, and then we divide it by f of r0. And so we start off, because f0 is just the normal polynomial, we start off with h0 of z is just going to be equal to g at r0 of z, because f0 is the same as f, and so we just have f of r0 e to the 2 pi I z divided by f of r0, so on and so forth, and that is the same thing as just inputting r0 into each of these. And then we also have it that h1 of z is going to be equal to f1 of z is just z to the n. And so we would have r0 e to the 2 pi I z quantity to the n divided by r0 to the n. what is this? This is going to be equal to r0 to the n times e to the 2 pi I z n. r0 to the n divided by r0 to the n cancels. We're just left with e to the 2 pi I z n, and we divide it by the magnitude of the exact same thing. So we divide it by the magnitude of e to the 2 pi I z n, but the magnitude of e to the 2 pi I z n is just 1. And so what are we left with? We are left with e to the 2 pi I n z, which is then equal to omega n of z, the loop that goes around n times, starting at 1. This family of functions, ht, is a homotopy. It's a homotopy that takes you from gr0, which we know is homotopic to e1 by this fact right here, and this homotopy takes you from that gr0 to omega n of z. And so by the transitive property of homotopy, we have omega n of z is homotopic to e1. Well, that's the constant map. The constant map is only homotopic to the loop that goes around 0 times. And so that means n is equal to 0. And so that means if n wasn't 0, f of z would have to have a root. And remember that we proved that each of these omega n's was in a different equivalence class while we proved the value of the fundamental group of the circle. And so this is directly related to that fact. Now, another expression of this is the Boyer's fixed point theorem. That's another application of the fundamental group of the circle. Why is this? Well, very quickly, let's go ahead and prove a lemma. The lemma is going to say, if you have a retraction R, look at the video where I introduced fundamental groups to figure out what a retraction is. Obviously takes you from x into a. And we have the inclusion map, iota, which takes you from a into x. Then iota star, the induced homomorphism, is injective. Why is this? Well, it's actually really easy. What you do is you do r composed iota star. This is going to be equal to r star composed iota star. But you could also view it as r composed iota. Now, iota maps all the elements of this beginning set A into X just onto themselves because it's the inclusion. But R moves all the elements of A to themselves by the fact it's a retraction. And so that means that this is the identity on A star. So that means R star is a left inverse of iota star. And by last time, we also know that R star is surjective. If the left inverse is surjective, that means that the map is injective. Okay, why is this important? Well, we can use it to prove that there is no retraction of the disk, the 2-disk, into the 1 circle. So there is no retraction that takes you from the filled-in disk and somehow moves you all, that moves all of them out onto this outer circle. There is no such retraction. And the reason why is because the inclusion, iota, from S1 into D2, what do we have? Well, we have iota star is going to be a map that takes you between their fundamental groups. That's by the definition of the induced homomorphism. This will be from the fundamental group pi 1 of S1 at some point into pi 1 of D2 at some point. But we know that this is non-trivial. And we know that D2 is a concave space. And concave spaces are simply connected, which means they are trivial. But if this is a non-trivial domain into a trivial codomain, it can't be injective. And so you couldn't have had this retraction. And so now that we've proven that there can be no retraction from the disk onto the circle, let's go ahead and prove Brouwer's fixed point theorem. So what Brouwer's fixed point theorem says is that if you have a continuous map that takes you from the 2-disk into the 2-disk, we have it that there exists a fixed point. So there exists an x in D2 such that f of x is equal to x. Why must this be true? Well, let's suppose it's not true. Well, I say that we can then construct a retraction. And this retraction is going to be, this is our disk, and any point x in our disk will have a brand new distinct point f of x for this continuous map f. From here, what we want to do, given the setup, we want to construct a retraction. How do we do it? Well, we have 2 points, and 2 points can create a line. Specifically, it can create a ray. So we do the ray that starts at f of x, goes through x, and then you look at that ray's intersection with the circle. And the reason I do f of x to x is because if x is on the circle, no matter where f of x ends up, the line will always intersect the circle, the boundary, at x. And so it's a retraction. It sends every element, x, of the disk onto an element of the circle, and it maps all the elements of the circle onto themselves. Now, the reason this is continuous is hard to prove rigorously, but you should be able to tell that because f is a continuous map by hypothesis, and because these are just constructed lines, and we know that lines are pretty continuous, that the perturbations should result in a continuous map. So, if you can trust me on that this is a continuous map, that is a retraction, but there can be no such retractions. Now, I'm going to prove another theorem involving circles and spheres, and it's the reduced version of the Borsuk-Ulam Theorem. So what the Borsuk-Ulam Theorem says is that if you have a continuous map f, which takes you from the sphere into R2, Euclidean space, then there exists some x, which is on S2, such that f of the antipodal point, negative x, is equal to f of x. There exists a point that maps to the same spot as its antipodal point. So, how do we prove this using the fundamental group of the circle? Well, we're going to do it in a similar way we proved the fundamental theorem of algebra. We're going to prove it by supposing it's not true. Suppose there does not exist such x. Then we're going to construct a special map that will come up with a contradiction. Let's go ahead and say g of x is going to be equal to f of x minus f of negative x divided by the magnitude of the same thing. So we have this map, which is never going to be equal to 0 because f of x is never equal to f of negative x. And so this denominator is never 0. Now the reason we divide it by its magnitude is so that it always has constant magnitude of 1. And so this map G will take in an element of S2 and output an element of S1. So this is a continuous map that takes you from S2 to S1. Now what we're also going to do is take a loop, eta, into S2. And this will just be the equator loop. So it'll be eta of S is going to be equal to cosine of 2 pi s, sine of 2 pi s, and then just 0. And so this is the one where on the sphere, it is just the loop that goes around this equator. So that's eta of s. Now what do I do with this? Well, eta of s is a loop, G is a continuous map. And so if I do G composed eta, this will be a map from I into S1, which is a loop in S1. And so I think you can see how we're going to prove the contradiction here. Now let's go ahead and call this H. G composed eta. Alright, so now what you should note is that G of x has a special property that I set it up with for this proof. Namely, G of negative x, G of the antipodal. What is that going to be equal to? Well, by definition, that's f of negative x minus f of negative x is f of x divided by the magnitude of f of negative x minus f of x. But, as you can see, this is the exact same thing as g of x, except these two are flipped on the top and bottom. Now the bottom, that doesn't matter, because you can take the negative of it it doesn't matter. It's a magnitude. The magnitude doesn't really care about the order of the subtraction. But on the top, what we have to do is compensate for that, and that is negative of g of x. What I want to do is transfer this property of g into h tilde, the lifting of h, which will be a map from I into R. How on earth do I lift this property? Well, first I have to do it for h. Well, let's think about this. We're doing g of eta of x. What we want to do is use the fact that g of negative something has to be equal to negative g of something. So that means that we want this input to be negative of eta of x. We want this input to be the negative of what it would normally be. So what we want to do is figure out eta of what value is equal to negative eta of x. Let's go ahead and think about this. If this is our equator, except we're looking at it top down, eta of x just takes you around it normally. So this is our angle x, and that's our point on the circle right there. Its antipodal point, its negative value, is going to be right over here. How do I get from there to there? Well, you can see from this diagram I drew, you want to add pi. So how do I get a value inputted into this parameterization where you add pi to the angle? Well, remember, eta of s is cosine of 2 pi s and sine of 2 pi s. And so if I wanted to go from 2 pi x to 2 pi x plus pi, well then I have to input x plus 1/2, because that is equal to 2 pi x plus pi. And so right there you have the same input you had before, except you add pi to the parameterization. And so this y right here is actually x plus 1/2. And so what all that gives you is that g of eta of x plus 1/2 has to be equal to g of negative eta of x is equal to negative g of eta of x. And so if you input x plus 1/2, you get the negative when you input x. And note that because eta is a loop, it can only go from 0 to 1. And so this only applies for x between 0 and 1/2. Because otherwise, if you say had like 3/4 plus 1/2, that's bigger than 1, not in the domain of eta. So what does this tell us about the lifting? Well, I know from the definition, p of h tilde of x has to be equal to g of eta of x. But what that tells me is that if I add 1/2 to the input, then this right here, by the fact I discussed before, has to be equal to negative g of eta of x, which is then negative p of h tilde of x. So that tells me that p of h tilde of x plus 1/2 has to be equal to negative p of h tilde of x. Or, in other words, that cosine of 2 pi h tilde of x plus 1/2, comma, sine of 2 pi h tilde of x plus 1/2 has to be equal to negative cosine of 2 pi h tilde of x, sine of 2 pi h tilde of x. But from the previous one, from eta, we know how to get the negative from this type of function. You add 1/2 to your input. And so to go from h tilde of x plus 1/2 to negative of h tilde of x, what you need to have is for h tilde of x plus 1/2 to be the value to make both of these negative for x, which would therefore be h tilde of x plus 1/2. So h tilde of x plus 1/2 is equal to h tilde of x plus 1/2. However, because we're dealing on R with this covering map, it's not just 1/2, it's all odd numbers q, every single odd integer q over 2. And so if you were confused by all of that, just know that h tilde of x plus 1/2 is equal to h tilde of x plus q over 2 for some odd integer q. And this is only going to apply for x between 0 and 1/2. And because this h tilde is lifted, this q can theoretically change over time. But we know that q over 2 is going to be equal to h tilde of x plus 1/2 minus h tilde of x, which is continuous, but q as an odd integer can only change discretely, which means q is constant. And that's a good news, because if I do h tilde of 1, by this identity, that's going to be equal to h tilde of 1/2 plus q over 2. And then h tilde of 1/2 is going to be equal to h tilde of 0 plus q over 2 plus q over 2, which is just q. So this tells you that h tilde of 1, which is the ending point of this lifting, is the starting point plus q. What this tells you is that h has to be homotopic to omega q. It has to go around q times, because the ending point of its lifting is q ahead of its starting point. And by the facts that we introduced last time, that means it's homotopic to omega q. Or, in other words, g composed eta is homotopic to omega q. What do I get from here? Well, I know that eta is going to be homotopic to just the trivial map, I'll call it ex0. Eta is homotopic to the trivial map ex0. This is just very basic, because you have the equator. If I just truncate the sphere at a point lower than it, so I just get rid of that, this right here, that path was contained in it. Right there, I can expand it out, and then this entire thing is homeomorphic to just the open circle in the real numbers, just expanding that out. And then I have a loop in there. Because it's concave, I can retract it. And so eta is homotopic to ex0. Let's go ahead and say it's homotopic by some homotopy h. Then I can do a homotopy g composed h. Because remember, h takes you from I cross I into S2, and then S2 to S1 right there. And so this would then be a homotopy from G composed eta to G composed EX0. But G composed EX0 is just E at G of X0. Now from before, we know that G composed eta is homotopic to omega Q. So that's homotopic to omega Q for some odd integer Q. But Q, because it's odd, cannot be equal to 0. And then we have a contradiction, because that's the loop that goes around an odd number of times, so it can't be 0, but this is omega 0. This is the one that goes around 0 times. By the facts that we introduced last time, that is impossible. And so it is a contradiction, and thus we have the Borsuk-Ulam Theorem. An interesting result of the Borsuk-Ulam Theorem, I'll call it a corollary 5, is that if I divide S2 into 3 different closed sets, A1, A2, and A3, each one of these closed, some AI contains some element x and its antipodal point. So how exactly do we approach this proof? Well, I'm going to use a collection of distance functions, di. The way we define the distance, di, of some point x, this will be the sort of distance between x and the set ai. And this is for I equals 1, 2, 3. So the way we will define this is the infimum for y, an element of ai. So all of the elements in ai, we take the smallest such value of the distance between y and x. So this is the smallest distance of any of the elements from x. So if this is a and this is x, the distance is this one here, because that is the smallest distance between A and X. So this DI is obviously going to be, these DIs are obviously going to be continuous maps from S2 down to R. And so if I take a pair of maps, D1 of X, D2 of X, this will be a map from S2 to R2, which means that there exists some X, an element of S2, such that D1 of negative X, D2 of negative X is going to be equal to D1 of X, D2 of X. Now, if either of these, D1 of X's or D1 of negative X's, is equal to 0, so if either of these DI of X's is equal to 0, that has to mean, by the fact that these AIs are closed, that means that X is an element of AI. But by the fact that DI of X is equal to DI of negative X for I equals 1 or 2, given the Borsuk-Ulam theorem, that means negative X also has a distance of 0 from AI, which means negative X is an element of AI too. But if D1 of X and D2 of X are both bigger than 0, what does that mean? Well, by the fact they are closed, that means X and negative X are not an element of A1 or A2 because they have the same distance and they're both bigger than 0. They are only an element of AI if their distance from AI is 0. That's equivalent conditions. But we know that the union of all three of these is the entire space. And so that means that if X and negative X are not an element of A1 or A2, that means they're both an element of A3. And so we get either one of those distances is 0, or we get that both of them are in A3. All right, so in this video, as a wrap-up, we proved the Fundamental Theorem of Algebra, the Brouwer fixed point theorem, and the Borsuk-Ulam theorem, as well as a corollary from it, only using the properties discussed in the previous video from the fundamental group. And these are just extraordinarily important theorems in topology and algebra. You can see how our dive into algebraic topology has direct applications to some of the most important theorems in math. Hopefully, this video just gives you more and more interested into algebraic topology and all of its different applications. Anyway, that's it.